Okay. This is a pretty important section that we're going to be working on tomorrow because I think we've pretty much wrapped up all of our limit stuff that we need to talk about, and now we're diving into the the meat of calculus, which is the derivatives and the integrals. And as you can see, this first objective that we're dealing with is pretty short. It's just a one-pager. But I'll be doing a lot of explaining, so I suggest taking extra notes along the side or on the top if there's something that I say that you think might be important, especially if I repeat it a couple of times. Alright, so objective, given the equation for a function relating to variables, we're going to estimate the instantaneous rate of change with respect to the independent variable at a given point. We're going to explain what some of that stuff means. Okay, the situation that I always use to start talking about derivatives is the door. If you push open a door that has an automatic closer, so like our classroom door is like this, it opens fast at first, then slows down, stops, starts closing, then slams shut. As the door moves, the number of degrees it is from its closed position depends on how many seconds it's been since you pushed it, which makes sense because time would have to pass in order for the door to be open at any given point. And as we talked about, as you push the door open, it's going to open really, really fast. And then at some point it's going to stop, and then it's going to start to close. And with an automatic closer, it always closes more slowly than how you opened it. And then at some point it probably stops and then closes and slams shut. Okay, so the figure below shows the door from above. And the equation, in this case, that's going to represent the degrees in terms of time, is d equals 200 times t times 2 to the negative t. Okay, the questions to be answered here are, at any particular instant in time, is the door opening or closing? And how fast is it moving? We can answer this question graphically and numerically. So if we suppose that the door is pushed open at time equals 0 seconds and slammed shut again at time equals 7 seconds, we're going to repeat this equation down here. While the door is in motion, we're going to assume that the number of degrees from its closed position is modeled by this equation. And the question is, how fast is the door moving at the instant when t equals, and actually we're not going to go 1 second, we're going to go 3 seconds. Now, whenever you're asking how fast, it's talking about velocity, or speed, but in this case velocity. So that question, how fast, has to do with some kind of rate of change. So like when you talk about a car going a speed, you say it's going in miles per hour. That's a rate of change. That's how miles change per hour. So we are looking at how the degrees are changing per second, or how fast it's going at the instant when t equals 3 seconds. And we're going to estimate it graphically and numerically. Okay, so the first thing that we're going to probably do here is make a graph. To save us some time, I'm going to give you a window. We know that my independent variable here is going to be time, and I was told that the door closes at 7 seconds, opens at 0. And then if we graph this function, so 200x times 2 to the negative x, I'm going to change my window, so we go from 0, let's go from negative 2 to 7, or let's say 8, just open it up a little bit, and then from negative 5 to 150. You get a graph going. Okay, so we have that graph. I'm going to go ahead and specify, I think that spot is 75, but, or not 75. Okay, so we get that sort of curve drawn. All right. we want to focus in on the time value of 3 seconds, or what's going on at the time value of 3 seconds. We can find what the degrees are at 3 seconds by actually taking 3 and plugging it in. So we would say, okay, at 3 seconds, degrees equal, okay, so that's just evaluating, and I think I can actually do it from this screen. If I plug in 3 for the function, I get 75 for my degree value. But that's not talking about how fast it is. That's just talking about how many degrees it's open at the particular instant of 3 seconds. This is not a rate of change. It's not a speed. It's just a value. The most common rate of change that we have dealt with in the past is slope, because slope is how the line changes as you rise over what you run. So slope is our most common rate of change that we've looked at. And since we don't have a line here, we're going to refer to the rate of change, in this case, being the slope of a curve. Okay, because we have something that's changing, not necessarily a straight line. So we're not actually finding slope of a line here because we don't have a line to deal with. But we can still think of rate of change as the concept of slope, or how steep maybe a curve is at certain values. Now if we look at it in terms of slope, if I was to look at this side of the curve, we would say that it has a positive slope, which makes sense because from 0 to about this time, whatever that is, the door is opening because your degrees are increasing. So because you're increasing, you're going to have a positive slope. And then from this point to 7, you have a negative slope. And that negative slope, or that negative rate of change, actually indicates that your door is now closing because your degrees are decreasing. Does that make sense? So when you talk about rate of change, in this case we're going to think about it as the slope of a curve, but in general rate of change is basically how much something changes over time. So like if you're talking about miles per hour, that's how the miles change over some unit of time. So in this case, as we begin to answer this question about how fast it's moving at the instant that t equals 3 seconds, we are going to think of it as how the degrees change over time, which looks like some kind of fraction or division problem, and how the rate of change is some kind of slope. And just to throw this out there, when we found slope in linear equations, like you stack and subtract, where you subtract the y values and divide it by the subtracted x value. Keep that in mind. Alright, so we are going to now approximate how fast the door is going at 3 seconds. We don't have the capability yet in calculus to find it at the instant of 3 seconds, but we can approximate by finding average rates of change. The reason we can't find it at the instant of 3 seconds is because whenever you find the slope of a line, you need 2 y values and 2 x values in order to do that. So you're always averaging, or you're always taking 2 values to come up with your how much something changes over time. It's not just one value. You can't take 3 and subtract itself because you can't divide by 0. So we're going to go ahead and set up a couple of problems here. The t values and the d values. Now, I have a time value of 3. We're going to use 3.1, 3.001, oops, that should just be 0.01, 3.001. Now when I set up this problem, I'm going to use slope as my foundation. As we already stated, I can't find the instant, because if I was looking at something at the instant of 3, your time, or like here you would subtract some y values, which we're going to find, and then you would subtract some x values to find the rate of change, or how much y changes over how much x changes. But if you're looking at the instant, essentially what you would be doing, and the problem would be trying to take 3 and subtract 3, because an instant is not a range of times, it's at one particular point. But whenever we find slope, we have to use some kind of range of value. So by picking values that are really, really close to each other, like 3.01, 3.001, really close to each other, you can narrow down to be very close to the instant, even though you're not at the instant. So that's where the limit concept comes into derivatives, is when you find the derivative, and that's actually what this is here, and we'll kind of brush up on that on the next page. Derivatives is finding the rate of change at an instant. But at this point, we have to get really close to that instant. We can't actually find it at that instant, because you always have to subtract y values and divide it by subtracted x values. So we're going to do 3 problems here. We're going to find the change in d over the change in t. This is like subtracting your y values over your subtracted x values. We're going to do this 3 times, just to see what happens. Okay, so in my calculator here, I'm going to go to the table and delete out all of these. I'm at 3, 3.1, 3.01, 3.001. Okay, so we're going to subtract these two. So you take 75 and subtract 72.31, changing your y values, divided by the change in your x values. One thing you have to be careful with here is whatever number you put first, you have to put the same number that's paired with it first on the bottom. So like 75 is the y value at 3. And that just makes sure that your positive and negatives are correct. Okay, and then we're going to subtract on the top, divided by the subtract on the bottom. When you do that, you end up getting negative 26.9. And we're going to include units here. So my change in degrees would be degrees, and then this represents seconds. So my first average speed or estimate of how fast it's going, you're finding the rate of change, or you're finding the slope of the curve between 3 and 3.1, those time values, and you get negative 26.9, which, if this is 75, looks like we're looking at that value there. Okay, then we're going to do the same thing with 3.01 and 3.1. Or actually, sorry, we're all basing it off of this 3. So then you take 75 and you use a y value that's a little bit closer. So we're going to go 3.01, which is 74.73. And then we have 3 minus 3.01. So we're getting a little bit closer to 3 by using this 3.01. If you do that, you get negative 27 degrees per second. Then we're going to get even a little bit closer to see if we can get even a better estimate. Of speed. And you end up getting negative 27 degrees per second. So we would say, okay, a good estimate, because I picked x values and y values that were getting closer and closer and closer to each other. We would say at 3 seconds, the door is closing, and the reason I know it's closing is because all of your speeds here, or your velocities, are negative, so you know your function is decreasing, so the degrees are decreasing. It's closing at a speed of negative 27 degrees per second. Okay. So as a rehash, when you're talking about rate of change, that's like finding slope of a curve. And at this point, because we can't find it at the instant of 3, because we can't take 3 and subtract 3, that would be what at an instant means, we have to find average rates of change, which is subtracting y values divided by subtracting x values. And if you pick y and x values that are really close to each other, like this 3.001, you're going to get a very accurate estimate. But it is still only an estimate. It's not the exact speed it's going at 3 seconds. Flip the page. You're going to cross this off because this is actually what we're going to be working on tomorrow together. For the door example, the angle is said to be a function of time, meaning you can't have an angle unless time has passed. Does that make sense? Time, we would say, is the independent variable. And the angle is the dependent variable. These names make sense. Why? Well, time is the independent variable because nothing stops or starts time. It's independent of everything else. And then the angle cannot increase or decrease unless time has passed. It's a logical conclusion we can make. The instantaneous rate of change, the dependent variable, is said to be the limit of the average rates as the time interval gets closer to 0. So, going back to this, as this time span gets less and less and less, so we could keep going, 3.0001, 3.000001, and we could keep going forever and ever and ever and have tons of decimals. The closer that time span gets to 0, so the closer you get to having 3 minus actually 3, the closer and closer your rate of change gets to the actual rate of change, where it's not an estimate anymore. That's why it's said to be the limit, because you're getting closer and closer and closer. The limiting value is called the derivative of the dependent variable with respect to the independent variable. So this value here that we found, it is the speed or the velocity of this situation, but that limiting value, which is what we would say if we looked at that as a limit, that is my derivative. So back up here where it says instantaneous rate of change, that means derivative. So derivative is just another word, but it's not just another word. The derivative is actually the instantaneous rate of change, not just rate of change. This is just rate of change. Instantaneous rate of change is being able to do this and actually subtract 3 minus 3 and find it at an instant and not have to average. So this is just estimations of the derivative because we still have to average. Eventually we'll get to the point where we can actually find instantaneous rates of change. Alright, so we just found average rates of change of fx over an interval of x values and used these to estimate the instantaneous rate of change at a particular value of x. The instantaneous rate is called the derivative of the function at that value of x. And then in this section we'll estimate instantaneous rates for functions using a graph, a numerical approach, as well as by equations. And then we're going to do some problems on that tomorrow, but at the very end here we're going to actually define derivative. Okay, so the derivative of f of x at x equals c is the instantaneous rate of change at x equals c. It is found numerically by taking the limit of the average rates as x approaches c. It's found graphically by finding the slope of the tangent line. We'll get into that a little bit more when we come back from break. but graphically by finding the slope of the tangent line at x equals